and welcome to the GeoDict 2021 tutorial on how to achieve high packing density of 80% with spheres in GeoDict. My name is Steffen Schwichow, Senior Graphics Designer here at Math2Market, and this tutorial has been originally created by Andreas Wiegmann, CEO of Math2Market. The result of this tutorial will be this sphere packing here with a packing density of 80%. First up, we open a fresh GeoDict 2021. Up here in the menu, we select Model and choose the GrainGeo module. The GrainGeo module creates digital 3D models of ceramics, sintered materials, grain packings or powders. From the drop-down list in the module section here, we select Pack Analytic Spheres. With a click on the Edit button, we open up the option dialog where we define what properties our sphere packing should have in the end. In the first tab, the Pack options, we define the packing density in the packing density field. By default, 0.63, meaning 63%, is set here. We want to achieve a packing density of 80% and change the volume in the field to 0.8. We create a new structure in a 300 by 300 by 300 voxel domain. The materials used are set by the material ID and the pore space is defined as air. The stop criteria for the solver is 1 million iterations or a runtime of 24 hours. The random seed here defines with which value the random number generator is initialized. To generate the same result as in this tutorial, you can enter the same value of 356. In the analysis here below, additional information can be stored. Next, we go to the Sphere Distribution tab. Here we see directly in the list that we have predefined two different types of spheres. To achieve our desired packing density of 80%, we need three different sphere types. In the unit selection above, we see that we currently specify all units in micrometers. So we have a sphere type with 100 microns, 50 microns, and we define another third sphere type with 10 microns, which will fill in the gaps. To add another sphere type, we click the up arrow in the Sphere Types field here and change the number of rows to 3. We set the sphere diameter to 10 microns. We also directly specify the volume probability of our three sphere types. These are normalized values, so the value here of 0.5 means a target distribution of 50%. For the 100 micron sphere type, we leave the volume probability at 0.5. For the 50 micron sphere, we set 0.3, and for the 10 micron spheres, 0.2. So in the end, we have a total value of 1, meaning 100%. In order to be able to easily distinguish the different sphere types later on, we set each type with its own material. To do this, we click on the Material button in the Sphere Types table, here at the back, and select the material for each sphere type from the Material Selector dialog. The choice of the material does not matter for the packing process. For the sake of simplicity, we will select a neighboring class material. Select, press OK, and repeat for the others until all have their individual material ID. Next, we define how many spheres will be used for packing. As we can see in the table under Achieved Distribution and Sphere Number, at the moment our probability inputs are practically ignored by the solver. The solver prioritizes the packing density, which we have specified as 80%. Considering all our settings, it can reach this goal most likely with these settings here. With the button Suggest Sphere Number, we can let the solver estimate with which number of spheres our desired result is most likely to be achieved. We click on it and see what is suggested to us. The solver suggests 2030 spheres, and we can see here that our specifications are met pretty well. However, so many spheres also require a long calculation time. We changed the value to 300 spheres. In this way, we no longer hit our targets as precisely as before, but we also do not have to wait so long for our result. A good compromise. With all settings set, we can now start the packing process. To do this, we click OK to save all settings and click Generate here. While the solver is working, we can see here in the graph which packing density the solver has already reached. For more detailed information, we can also use this button here with the two arrows to display the iterations, the achieved packing density and the runtime in detail. To put the speed into perspective, the specifications of the computer on which GeoDict is currently running for this tutorial are shown here. With now just below 80% achieved packing density, the solver now needs most of the time to achieve the last few percentage points by small displacements of the spheres. If there is no improvement of the packing density over several iterations without the spheres penetrating each other, the solver aborts and notes the reason for the abort in the result GDR. For the random seed set, our 80% should be relatively quickly reached. Any second now. The result viewer opens automatically at the end of the calculation and gives us again an overview of the used parameters, like here the number of spheres, the achieved values, here the final packing density, and some analysis, here the 364 contacts among the spheres. Under plots, we can look at the convergence curve, the packing density achieved over the runtime. We can clearly see that the first 60% of the packing density was achieved in a quarter of the time, and the last 20% took a good 3/4 of the time. The result structure was loaded automatically, but can also be loaded here using the Load Structure button. Initially, our microstructure is displayed in a 2D mode. The representation of our microstructure is analytical, which means that the spheres are not only available in voxel form, but as analytically described objects with all information about diameter, center coordinates, and etc., and can also be viewed individually. Thus, the spheres can also be represented periodically in the domain. We have only one of the 100 micron sphere here in red in our domain, but we see one here and one here. This is actually the same sphere leaving the domain here and reappearing here. The same thing happens, clearly visible, with the green spheres here and here. And of course with the yellow spheres as well. More information about our domain can be found up here. Our domain, as previously defined, is 300 by 300 by 300 voxels in size, with a voxel length of about 351 nanometers. The voxel length is calculated based on the size of the spheres and the size of the domain. In 2D mode, we can move through our sphere pack via the slice slider by pulling the handle here. In the statistic tab up here, we can see that we have overall 20% of the volume represented as pore space. And if we open the drop-down list by clicking on it, we can see that we have around 44% of the volume in the form of the red sphere, 22% of the volume in form of the green spheres, and 13% of the volume in yellow spheres. Additionally, here we have a volume distribution based on the materials instead of based on the material IDs. And over here, the same statistics but related to the current slice in our 3D view. We can also view our sphere pack in 3D by switching to 3D mode via the toolbar icon here, or the menu under View and 3D Rendering. Here we see in detail how the packing density was actually achieved. The small yellow spheres fill the empty spaces between the large red and green spheres. The red and green spheres together achieve about 67% of the packing density. And together with 13% yellow spheres, we achieve our high packing density of 80%. Thanks for watching. We hope you enjoyed this tutorial and check back for the next one. Goodbye.